Forget what you think you know about artificial intelligence. Forget the chatbots and the image generators. The real story isn't about the apps on your phone. It's about the single greatest build-out in human history. And it's happening right now. We are in the process of building a global machine that can think, and the price tag for this ambition is staggering. The total investment in the infrastructure needed to power this revolution is projected to hit $7 trillion by the end of the decade. To put that in perspective, for that price, you could fund the Apollo program 27 times over. You could build the International Space Station 45 times. You could run 230 Manhattan projects all at once. This isn't just an investment, it's a fundamental reshaping of our planet's infrastructure. A collective, high-stakes bet that the future of economic growth lies not in human hands, but in silicon circuits. The question is it sustainable? Well, let's find out. Most people only experience AI at the application layer, chatbots, copilots, search. But that's just the tip of the iceberg. The full ecosystem is a multi-layered, resource-intensive stack, each layer involving tens or hundreds of billions in annual capital and operational expenditure, not to mention a significant draw on energy and natural resources. It all starts with sand, the raw material for silicon, which is transformed in semiconductor and memory fabrication plants, or fabs. Building and operating these fabs is an astronomically expensive endeavor. Semiconductor capital expenditures are dominated by just 3 companies: Samsung, TSMC, and Intel. In 2024 alone, semiconductor capex is estimated to be around $155 billion. SK Hynix, Micron, and Samsung are the main players in high bandwidth memory. The next layer is where the magic really happens: processor manufacturing. And in this realm, one name reigns supreme. Apple and Microsoft took several years to go from a $1 trillion market cap to 3. Nvidia did it in a matter of months. Of course, competitors are trying to break this hold. AMD is fighting for a piece of the pie, while US sanctions have forced Chinese firms to develop their own in-house alternatives. Even tech giants are getting in on the action, with Google's Tensor processing units and Amazon's Trainium chips, all designed to reduce reliance on Nvidia. The output of this layer is high-performance compute chips called AI accelerators, or GPUs. A GPU's power is measured in flops, or floating point operations per second, with the latest chips capable of performing trillions of calculations in the blink of an eye. Next up is the model layer. Training large language models requires an immense parallelized computing effort from tens or even hundreds of thousands of interconnected GPUs. These training clusters, housed in massive data centers, are some of the most power-hungry structures on Earth. Take, for example, xAI's Colossus supercomputer in Memphis. It's one of the largest currently operational AI training platforms, built in just 122 days. This single computer requires hundreds of megawatts, enough energy to power approximately 250,000 homes. But even that pales in comparison to what's coming. OpenAI's planned $500 billion Stargate project is targeting 10 gigawatts of compute capacity, 50 times that of Colossus. Once these models are trained, they enter the application layer, serving up intelligence in the form of tokens, which software companies can then integrate into their products, effectively embedding a thinking machine into their software. The massive capital pouring into this sector is a collective bet on one thing: the value of a token. The investment landscape breaks down into 2 main categories. First, you have equity and private capital pouring billions into training and deploying models. OpenAI, for instance, has seen its valuation skyrocket, raising tens of billions in funding. They are projected to generate $12.7 billion in revenue in 2025 alone. Then, there's the massive capex from the hyperscalers, the tech giants building the foundational infrastructure. This is where you see projects like Stargate, a clear indication of the long-term, multi-trillion-dollar commitment to building the backbone of the AI economy. But it's not just about the headline projects. Amazon is spending over $100 billion in AI infrastructure in 2025. Microsoft allocated $80 billion. Google bumped their spending to $75 billion. and Meta is spending up to $72 billion. All this spend is a collective bet that the tokens will be worth more to users than they cost to produce, by a lot, and soon. When you look at the trillions being poured into AI by the biggest companies on Earth, it's easy to see just how massive the build-out is. But how do we make sense of the direct economics of what these investments produce? One way is to boil it down to 3 simple metrics. Dollars per watt, the cost of the immense energy required to power these systems directly tied to energy production and infrastructure. Dollars per flop, the cost of compute. This cost is continuously decreasing as the hardware and software running AI models becomes more efficient. Akin to Moore's law, GPU price to performance has been doubling about every 2.5 years since 2006. And finally, dollars per standardized token. As models become more efficient in data, compute, and energy usage, the cost per token drops. This figure reflects not just compute, but also memory, networking, orchestration, and the amortized costs of model R&D and licensing. Another useful angle to view AI is by analyzing a model as a single venture in itself. The balance between R&D, training, and inference costs per token versus the revenue earned per token. As Dario Amodei of Anthropic has explained, most losses are associated with continued scaling and development of future models that have yet to be released. The entire AI stack is priced by the value of a token. The ultimate question is someone willing to pay more for that token than it costs to produce? Right now, most AI product companies are highly unprofitable. OpenAI, for example, does not forecast being cash flow positive until 2029. They reported a staggering loss of $5 billion in 2024 alone. So where does revenue come from? What is AI actually being used for today? Recent usage reports from OpenAI and Anthropic give us a glimpse. A significant portion of ChatGPT's use is for personal tasks, with 70% of conversations being non-work related. Coding assistance, however, dominates the use of Anthropic's Claude, a much more valuable use case. The ultimate end goal of enterprise AI adoption is a massive increase in productivity. A recent research paper from OpenAI called GDP-Val set out to measure just how big that increase could be. The study looked at 1,470 real-world tasks that would take an industry expert on average nearly 7 hours, with average costs of almost $400. In comparison, an AI model could produce a comparable deliverable in about 4 minutes for less than $4. That's a 100-fold increase in speed and 100-fold decrease in cost. Human experts then blindly judged both the human's output and the AI's output and picked their preferred deliverable. Now, even though the AI's output was preferred only about 1/3 of the time, the observed significantly reduced costs for the first time proves a crucial point. For the average economic task, it's slightly more efficient to have a human expert prompt an AI, review the output, and make corrections than it is to do the entire task from scratch. This holds true even if the model occasionally fails so badly that the human needs to start over anyway. Increasing the average productivity of every knowledge worker in the world by just 1% would result in gains of around $500 billion a year. According to this study, with the right approach, AI integration currently increases productivity by over 30% for the average digital task. As models continue their steady trend of becoming more intelligent and reliable, this collaborative approach will become increasingly more time and cost-effective for virtually every knowledge work task. But this research also comes with a critical warning. Of the outputs that were deemed inferior to the human, 1/4 were reviewed as bad, and almost 3% were catastrophic. This is a clear indicator that for now, expert human oversight is absolutely essential. We're not yet at a stage of fully autonomous AI agents for complex or high-stakes economic work. The reliability simply isn't there yet. If you focus on one standard output, like a research paper, for example, and assume one person is responsible for creating this product, there is a single sum of work required to produce said product. Let's assume there is more work required than a single person is currently capable of. It is that person's responsibility to employ capital to outsource whatever remaining work is lacking. The capital can either be employed by hiring a human assistant or purchasing some means of automation. It is this person's responsibility to employ the most time and cost-efficient method to fulfill this void. As the capacity and cost of automation inevitably improves over time, it is in the person's best interest to shift more capital to automation rather than human assistance. The end result of this is that the time and money required to produce a research paper drops over time. Fewer human assistants are needed, and more total research is produced. There will be areas that are more prone to automation than others. As these become automated and more total product is created, bottlenecks needing more human expertise will appear elsewhere. Total work to be done remains elastic. With rapidly increasing automation, productivity per person will skyrocket, but the value of capital is likely to increase much faster than the value of labor. A distinct advantage is granted to those with excess capital, as increasing value will naturally accrue to capital. So, we return to our initial question: is this massive build-out sustainable? The honest answer is, we don't know yet. We are in the middle of the most aggressive and expensive technological wager in human history. The trillions being invested in AI aren't just building data centers. They are laying the foundation for an entirely new economic reality. For a century, economic growth has been tied to human productivity. That fundamental link is now being tested in real time. The GDP Val study gives us the first concrete glimpse into this future, a world where the cost of knowledge work plummets, and the speed of innovation accelerates beyond anything we've ever witnessed. This isn't just about making businesses more efficient, it's about fundamentally increasing the total amount of discovery and creation that is possible. This is what's fueling the multi-trillion-dollar bet. The belief that for every mundane report, every line of code, and every complex design, there is a cheaper, faster, and more efficient way forward. Yes, the transition will be disruptive. As automation absorbs tasks, the value of capital will skyrocket, creating new economic pressures. The challenge will be to ensure that the immense wealth generated by this infrastructure doesn't just accrue to its owners, but also empowers the human workforce to tackle the new, more complex problems that will inevitably emerge. This isn't the end of human labor, but a radical redefinition of it. We are moving from being the producers of work to the directors of it, the strategists, the ethicists, and the final quality check on an engine of unprecedented power. The AI revolution is here. The build-out is happening, and it's poised to unlock a wave of progress that will dwarf every technological leap that has come before. The real question isn't whether AI will be profitable. The titans of tech have already decided it will be. The question is, as we build these new engines of creation, what is the role for the rest of us in the world they are creating?